Heat, hot and cold. Woolen fibers have a number of crimps or bends. Air enclosed within the woolen clothes does not allow body heat to escape, and this keeps us warm. When we call something hot or cold, the question arises, how hot or cold it is. The amount of hotness or coldness of a body is called its temperature. For example, in summer, if the days are hot, the weather report on the TV tells us that the maximum temperature recorded is 38.2 degrees Celsius. And in winter, the weather report tells the lowest or minimum temperature recorded. It can be easy to make out the amount of hotness or coldness by comparing these two weather bulletins. Why and when do we feel hot or cold? To understand this, we first must learn about hot and cold. Hot and cold. Hot and cold are sensations that our body detects or we feel with respect to our surroundings. During summer, our surroundings become hotter than our body, and we feel hot. During winter, the surroundings become colder than our body, and we feel cold. Hot and cold are therefore relative terms in relation to our body temperature. However, our body is not perfect in differentiating hot and cold. Based on our body sensation, we use words like cool, cold, warm, lukewarm, and hot. If an object or our surrounding is at a slightly lower temperature than our body, we say it is cool. If it is at a much lower temperature, it is called cold. On the contrary, an object having slightly higher temperature than our body is called lukewarm or warm, and if the temperature is much higher, it is called hot. Take 3 containers and arrange them in a row on the table. In the first container, fill some ice-cold water. Put some tap water in the second container and put some hot water in the third container. Dip your left palm in the cold water and dip your right palm in the hot water and keep them dipped for some time. Now, take out both your palms and put them together in the container containing tap water. The tap water will feel warm to the left hand and cool to the right hand. The same water appears cold and warm both. This is because hot and cold are relative to the sensation of your body feels or detects. Heat and its flow. Heat is a form of energy which, when acquired by a body, makes its temperature rise. When we light a stove at home to cook food, the chemical energy stored in the cooking gas or any other fuel gets converted into heat energy on burning. This heat energy is then used to cook food. Similarly, we can convert electrical energy into heat energy when we use an electric heater. If we rub our palms together during winter, the mechanical energy gets converted to heat energy and our palms feel warm. Thus, heat is neither produced nor destroyed, and being a form of energy, it gets converted from one form to another. How does an object get heated? You are aware that any kind of material, whether a solid or liquid or gas, is made of small particles called molecules. When heat is applied, the molecules of the material gain energy and begin to move from their position. In this way, the material begins to get heated. The movement of the molecules also transfers the heat in the material. This system of molecules is different in solids, liquids, and gases. Heat flow in solids. Solids have tightly packed molecules that do not have free space to move. When solids are heated, the surface of the solid, which is in touch with the heat source, receives the heat energy and its molecules begin to vibrate due to the heat energy. As the molecules are tightly packed, the energized molecules knock against each other and pass on the energy to the other neighboring molecules. In this way, heat is transferred in the entire body of the solid. This form of heat flow or heat transfer is called conduction. Solids that conduct heat are called good conductors or simply conductors, while those that do not conduct heat are called bad conductors or insulators. The transfer of heat in solids is like the passing of the bus ticket from the bus conductor to the passenger sitting on the last seat. The ticket is passed on from one passenger to another till it reaches the last passenger. Heat water in a small pan or a beaker. Collect some different articles such as steel spoon, plastic scale, pencil, and divider. Dip one end of each of these articles in hot water and wait for few minutes. Then touch the other end. You will observe that spoon made of steel gets hot while the pencil made of wood does not get hot. Article: spoon. Material of article: steel. Does other end get hot? Yes. Pencil. Wood. No. Heat flow in liquids. The molecules in a liquid are loosely packed as compared to solids. That is why liquids do not have a definite shape like solids. The molecules are free to move from their position. When a liquid is heated, the molecules in contact with heating source gain energy and begin to move from their place. As these energized molecules move from their place, the other non-energized molecules begin to occupy their place, and they too absorb the heat energy. This type of heat transfer in materials, in which the molecules move from their place to enable flow of heat, is called convection. The transfer of heat in liquids is similar to the bus passengers in a bus who get up from their seat individually and go to the conductor's seat to get their tickets. Each passenger individually receives his or her ticket by moving from his place to the conductor. Take a beaker and fill it half with water. Set up an assembly of a burner, a stand, a wire gauze, and put the beaker containing water on the burner. Add a few crystals of potassium permanganate. As the water begins to heat, what do you observe? The crystals of potassium permanganate move up and down in the water and begin to dissolve, making the water purple in color. This activity shows that heat is transferred within the liquid by the movement of particles, molecules, in a cyclic up and down manner. This type of heat flow in liquids is called convection. Heat flow in gases. Convection also occurs in gases. In fact, places near the sea coast have a maritime or marine climate with strong winds blowing day and night due to the process of convection. In order to understand convection in gases, we should perform a simple activity. Take a large cardboard box. Cut 2 holes on the top of the box. In these holes, attach 2 cylindrical cardboard pieces and paste them firmly. Take a burning candle with a proper base and put it below one hole and close the box tightly. Make sure that candle flame does not put the cardboard box on fire. Take a dhoop batti or agarbatti, light it and put the burning part near the other hole. Smoke from your agarbatti or dhoop batti will be drawn into the box through the hole and come out of the other hole below which you have lighted the candle. This happens because the air above the candle absorbs heat and gas particles, after gaining energy, move upward. This creates a low air pressure around the flame, and fresh air is sucked in through the other hole to keep the candle burning. This cyclic movement of air starts a convection current, and the smoke from the dhoop batti or agarbatti is sucked in through the other hole along with fresh air. Similar to the activity you have performed is the phenomenon of land and sea breezes. These breezes occur on the sea coasts and are based on the principle of during the daytime, land near the sea heats up faster than the sea water. The air above the land absorbs this heat and moves up due to convection, just as the air above the candle in the box moves up. When the air above the land rises up, it creates a pressure change, and cool air from the sea comes to fill up its place. This mechanism of a cool breeze blowing from the sea to the land during the daytime is called sea breeze. At night, a reverse or opposite phenomenon occurs when the wind blows from the land to the sea. At night, the land cools down faster than the adjoining seawater. The seawater is warm and the air above the sea absorbs this heat. A convection current starts due to which the warm air above the sea rises up, creating a pressure difference between the sea and land. Air masses from the land blow towards the sea to take the place of the rising air. This mechanism of a cool breeze blowing from the land to the sea during night is called land breeze. Heat flow without medium. You have seen how solids, liquids and gases transfer heat by absorbing the heat energy themselves. Heat is a form of energy, and therefore heat is transferred from its source to the surrounding without the need of any solid, liquid or gaseous medium. Between the Sun and our planet Earth, there is no medium for lakhs of kilometers. The atmosphere is only about 500 kilometers thick, which contains gases. The Sun's energy travels through space like all other forms of energy. On reaching the Earth, some part is reflected back from the atmosphere, and the remaining useful part crosses through the atmosphere and directly heats the Earth's surface, including us. The Sun's rays do not directly heat the air. This kind of transfer of heat from the source to another body without affecting the medium is called radiation. To verify the process of radiation, recall the cold winter day. The air temperature is low and you feel cold. When you sit outside in the sun on a cold day, your body directly absorbs the sun's heat and you feel warm. However, the sun's rays do not heat the air around you. This is a clear example of radiation. In a similar manner, the heat from a bonfire warms you in a cold night when you stand close to it, but the air does not absorb much of this heat. This activity will explain the concept of radiation in a more scientific way. Take two thermometers in a garden. Hang one thermometer on the branch of a tree in a shade, such that its bulb is freely suspended. Dig out some soil in an open area near the tree on which you have hung the thermometer. Now place the bulb of the second thermometer about 2.5 cm in the ground where you have dug and cover the bulb with soil. Support the stem of the thermometer by a stick or some other support. Leave the two thermometers in their positions till late afternoon. The thermometer buried in the ground will have a slightly higher reading than the one hung from the tree. This is because the earth is heated directly by radiation without affecting the air or the medium in between. Thus, there are three ways by which heat is transferred from one body to another. They are conduction, convection, radiation. Effects of heat. Heat causes the increase in temperature. Heat causes expansion. Heat causes the change of state. Heat causes chemical changes. Heat affects the living organisms as it may cause death to microorganisms. Measurement of heat. Heat is a form of energy and is also called thermal energy. Energy is measured by its capacity to do work. Thus, heat is measured in a unit called joule, named after the famous scientist Joule. We measure the degree of hotness or coldness of a body as temperature. Thermometer is an instrument used for measuring temperature. In the 17th century, temperature measuring device was called thermoscope. It consisted of a wine container which was attached to an inverted flask with a long stem-like neck. The round bottom of the container was slightly heated. This led to expansion of air inside, which bubbled out of the wine, resulting in a rise of wine in the stem-like neck of the container. The thermoscope could detect appreciable change in temperature by the change of the wine level in the stem of the flask. In the early 18th century, Daniel G. Fahrenheit, a German physicist, designed the thermometer with mercury in a sealed glass tube. This thermometer resembled the modern thermometer and had 212 divisions. Later, mercury and alcohol, both kinds of thermometers, started being invented, and the system exists even today. There are two types of commonly used thermometers. One is an ordinary thermometer that may contain alcohol or mercury, and the other is clinical thermometer containing mercury. Other than these, there are specialized type of thermometer used for different scientific and industrial applications. Temperature is measured in degrees by three different scales. The scale commonly used by people in cold countries like America and some European countries is the Fahrenheit scale, after the name of the inventor of modern thermometer. This scale is divided into 180 divisions or degrees. Another popularly used scale is the Celsius scale. This has 100 divisions or degrees. The third scale to measure temperature is called the Kelvin scale. This is used in scientific research. All common thermometers are marked based on the temperature of the boiling and freezing water. Thus, in the Fahrenheit scale, water freezes at 32 degrees Fahrenheit and boils at 212 degrees Fahrenheit. In the Celsius scale, water freezes at 0 degrees Celsius and boils at 100 degrees Celsius. In the Kelvin scale, the 100 divisions begin from 273 Kelvin. In this, water freezes at 273 Kelvin and boils at 373 Kelvin. Degree is not mentioned as a convention. To verify the freezing and boiling temperatures of water, perform these two activities. Take a round bottom flask and put some distilled water in it. Close the flask with a stopper having two holes. Pass a bent L-shaped glass pipe through one hole and a laboratory thermometer through the other. Make sure the bulb of the thermometer is immersed in the water when the stopper is closed. Put the flask on a tripod with a wire gauze and heat it with a burner. Note the temperature of water before heating. Again, note the temperature of water when it boils. The temperature of boiling water is 100 degrees Celsius. This is called the upper fixed point. Take a glass funnel and fix it on a stand. Place a beaker below the funnel. Take some ice cubes from the refrigerator and put them in the funnel. Carefully place the bulb of a thermometer between the ice cubes and fasten it to a support on the stand. Leave the setup for a few minutes. As the ice begins to melt, you will see drops of water falling from the funnel into the beaker. Before all the ice melts, note the reading of the thermometer. The melting point of ice is 0 degrees Celsius. This is called the lower fixed point or the melting point or the freezing point. Clinical thermometer. Clinical thermometer is designed to measure the temperature of human body. It has the range of 35 degrees Celsius to 42 degrees Celsius, as temperature of human body normally lies between this. A clinical thermometer consists of a long, narrow, uniform glass tube. It has a bulb at one end which contains mercury. Outside the bulb, a small shining thread of mercury can be seen. The thermometer uses a scale to give the reading of the temperature of an object or material. The scale we use in a clinical thermometer is Celsius scale, in which reading is noted in degrees Celsius, which is also written as degree C in short, along with its number value. A clinical thermometer reads temperature from 35 degrees Celsius to 42 degrees Celsius. Reading a thermometer. For reading a thermometer, note the temperature difference indicated between these marks. If the bigger mark reads 1 degree and there are 5 divisions between them, then one small division can read 1 degree Celsius divided by 5 is equal to 0.2 degrees Celsius. The thermometer must be washed with an antiseptic lotion like Dettol or Spirit. Then hold it firmly and give it a few jerks as to bring the level of mercury down below 35 degrees Celsius. Now, place the bulb of the thermometer under your tongue. After 1 minute, take the thermometer out and note the reading. It gives the reading of your body temperature. The temperature should always be stated with its unit, degree Celsius. Precautions to use a clinical thermometer. Thermometer should be washed before and after use, preferably with an antiseptic solution. Before use, 2-3 jerks should be given to the thermometer to keep the mercury level below 37 degrees Celsius. While giving the jerks, care should be taken that the thermometer does not hit any other object. While the thermometer is inside your mouth, do not laugh or talk so as to prevent the breaking of thermometer, which may release mercury. Mercury is poisonous and fatal to life. Read the thermometer keeping the level of mercury along the line of sight. The thermometer can be given small rotation to make the capillary and the level of mercury clearly visible. Do not hold the thermometer by the bulb while reading is taken. Laboratory thermometer. It consists of a very thin capillary tube of glass which is surrounded by very thick, supportive glass balls. The upper end of the capillary is closed after evacuation and the lower end is drawn into a delicate bulb-like shape with a thin glass ball. The range of a laboratory thermometer is generally from -10 degrees Celsius to 110 degrees Celsius. Converting one temperature scale to the other. The figure given here clearly represents the relation between the 3 temperature scales. If in a thermometer, mercury rises and the corresponding readings on Celsius and Fahrenheit scale are degree Celsius and degree Fahrenheit respectively, then temperature ice point divided by steam point ice point C minus 0 upon 100 minus 0 is equal to F minus 32 upon 212 minus 32. C upon 100 is equal to F minus 32 upon 180 is equal to temperature in Kelvin is equal to C plus 273. In the given relation, if temperature in degree Fahrenheit is taken on the left-hand side of the equation, then the right-hand side of the equation will be for degree Celsius and vice versa. Steam point 100 degrees Celsius, 212 degree Fahrenheit, 373 Kelvin. Ice point 0 degrees Celsius, 32 degree Fahrenheit, 273 Kelvin. Celsius scale, Fahrenheit scale, Kelvin scale. Example. Convert 40 degrees Celsius to degree Fahrenheit. Temperature 40 degrees Celsius. Steam point 100 degrees Celsius. Steam point 212 degree Fahrenheit. Ice point 0 degree Celsius. Ice point 32 degree Fahrenheit. Putting the values in the relation 40 minus 0 upon 100 minus 0 is equal to x minus 32 upon 212 minus 32, or 40 upon 100 is equal to x minus 32 upon 180, or 100 into x minus 32 is equal to 180 into 40, or 100x minus 3200 is equal to 7200, or 100x is equal to 7200 plus 3200. X is equal to 10400 upon 100, or x is equal to 104 degrees Fahrenheit. Therefore, 40 degrees Celsius is equal to 104 degrees Fahrenheit. You can test this answer by putting the answer in the relation again. This time, temperature is 104 degrees Fahrenheit. Steam point is 212 degrees Fahrenheit. Steam point is equal to 100 degrees Celsius. Ice point is equal to 32 degrees Fahrenheit. Ice point is equal to 0 degrees Celsius. Thus, 104 minus 32 upon 212 minus 32 is equal to x minus 0 upon 100 minus 0, or 72 upon 180 is equal to x upon 100, or 180x is equal to 7200, or x is equal to 7200 upon 180, or x is equal to 40 degrees Celsius. Therefore, 104 degrees Fahrenheit is equal to 40 degrees Celsius. The real test of this simple relation is to find a temperature which is the same in degree Fahrenheit and degree Celsius. Here in this case, degree Fahrenheit is equal to degree Celsius. So, temperature is equal to steam point is equal to 100 degrees Celsius. Steam point is equal to 212 degrees Fahrenheit. Ice point is equal to 0 degrees Celsius. Ice point is equal to 32 degrees Fahrenheit. X minus 0 upon 100 minus 0 is equal to x minus 32 upon 212 minus 32, or x upon 100 is equal to x minus 32 upon 180. X into 100 minus 32 is equal to 180x. 100x minus 3200 is equal to 180x. 100x minus 180x is equal to 3200. Minus 80x is equal to 3200, or x is equal to minus 3200 upon 80 is equal to minus 40. Degree Celsius is equal to degree Fahrenheit is equal to x. Minus 40 degrees Celsius is equal to minus 40 degrees Fahrenheit. Materials and their heating property. Materials that allow passage of heat easily through them are called good conductors. Materials that do not allow passage of heat are bad conductors or insulators. You have also read that metals are generally good conductors, while liquids and gases are poor conductors. It is important to know that the ability of a material to conduct heat depends on the nature and property of the conductor. Some materials that are conductors transfer heat very fast, while others take a longer time. Let us take the example of some common metals such as silver, copper, aluminium, and iron. All are metals and are good conductors of heat, but they have different rates of conducting heat. Metals that are good conductors, having low specific heat, absorb heat faster by conduction and cool down faster also by radiating the heat. This property of good conducting metals is used to make heat exchanger for engines, air conditioners, and refrigerators. You may have noticed a black-colored filter-like device in front of car engines, where water is filled up to cool the engine. It is called radiator. The radiator is made of these pipes. Water is circulated in the engine through pipes. Heat from the engine is rapidly absorbed by the copper pipes, which heat water. The heated water is then passed on through a fine network of copper pipes, where the heat is radiated. Thus, the cooled water is recirculated and the car engine is cooled continuously. Heat circulation in the atmosphere. The sun's heat reaches us by the process of radiation, during which the air of the atmosphere is not directly heated. The temperature of the air comes from indirect heating. The sun's rays heat up the earth and the objects on the surface of the Earth by radiation. The Earth, having a lower specific heat than water or air, heats up faster. The heated Earth then radiates out its heat, which in turn is absorbed by certain gases in the air. These gases retain the heat during night when the sun's heat is not received. It is due to this reason that the atmospheric temperature does not fall all of a sudden in the absence of sunlight. Thus, our atmosphere acts as a blanket, allowing limited heat radiated by the sun to come to the Earth. Also, the atmosphere retains or holds back the heat and does not allow all the heat to escape. This role of the Earth's atmosphere is called the greenhouse effect. It is beneficial for the maintenance of a constant range of temperature on the Earth, which is necessary for life to exist. Gases such as carbon dioxide, methane, and many other gases trap the heat and are called greenhouse gases. In the present time, with the advancement in technology, man has artificially increased the amount of greenhouse gases in the atmosphere. Under natural circumstances, the carbon dioxide is 0.02%, which is in balance due to the natural cycle with the help of green plants. But man has increased the release of carbon dioxide, methane, and other greenhouse gases on one hand, and reduced the forests that absorb carbon dioxide on the other. The result is that the atmosphere has warmed up over the years, and this is called global warming. Global warming has its ill effects. A slight rise in atmospheric temperature may result in the melting of polar ice in the Antarctica and Arctic regions. This may lead to increase of water in the oceans, which may in turn submerge land at the sea coasts. It would mean the sea coming in and reducing the land available to us. It is therefore our responsibility to check pollution and prevent destruction of forests.